Good morning, good afternoon. My name is Lennart Stahl, and I will, together with Wayne DeClosa and Vikas Dumi, do this presentation. The purpose of this, the title of the presentation is covering what we're going to talk about. It's considerations when designing a non-residential heat pump system to comply with ASHRAE Standard 15. And this is a follow-up on the previous presentations. In March, we did an Expo presentation about Standard 15.2. That's for residential. So this will be similar, but now we're going to focus on Standard 15 instead. In April, we had a webinar about Design Simulator for R32 systems. And last week, Vikas did an Expo presentation about the new R32 system J7S. Housekeeping, if you have questions, type them in. We will answer as we go or wait until the end if we have time. Introduction, that's what's going on right now. And then, of course, an overview of A2Ls and the Standard 15 itself. And then how to apply the Standard 15. Going to have some good examples in the later part of the presentation, and then a couple of takeaway slides to summarize. You can see some questions on that slide, and that's what's going to be. We're going to try to answer those and cover those. The most important ones are probably at the top there. I put them at the top. That's what's the maximum allowed refrigerant charge for a room according to Standard 15, and do we need leak detection always or not? That, together with the rest of those questions, we're going to discuss. A2L refrigerants, so I'm sure you heard about it, and this will just break it down a little what they are. So right now there are 6 of them approved by EPA. We discussed R32 here, we focused on that, but there's more of them there. They all have a GWP, global warming potential, below 700, ODP, ocean depletion potential of 0. The 2 in A2L indicates that they are mildly flammable. The L indicates that they have low burning velocity. But for an A2L refrigerant, for any of those to ignite, 4 conditions has to be met. It needs to be high enough minimum ignition energy, MIE. Cigarettes, toasters, electric heaters, and other common household products will not ignite an A2L. Also need to have a high enough temperature for R454B, it's 925 degrees. For R32, it's 1190. So R454B will ignite earlier at a lower temperature than, for example, R32. Need to have a certain concentration, 14 to 31% for R32, and a constant supply of oxygen. If any of those 4 conditions aren't there, it's not going to ignite. You also heard that it is flammable and have a slow flame speed. The flame speed for all these is approximately 0.15 miles per hour. Compare that with the walking speed that's typically 3 miles per hour, so you can walk 20 times faster than the flame speed for this refrigerant. Actually, I googled how fast people crawl, and the answer was 0.3 miles per hour, so you can still crawl twice as fast as the flame speed for this. On the next slide, we're going to look at the timeline for the A2Ls. Right now, we can look at the upper part there. The non-A2Ls, 410A, for example, can still be installed, but it has to be manufactured and imported before January 1st this year. And that's for small system below 65,000 BTUs. They can be installed during this year, then it has to be done. It's a little different, kind of delayed for non-A2Ls above 65,000 BTUs. They have to be manufactured and imported before January 1st, 2026. Then they can be installed the following year or 2027. It depends on when they got the permit. If they're permitted late, kind of on or after 10/5/23, then they can be installed during 26. If they have an earlier permit, then they can be installed during 27. So end of 27, all of it has been done. And these are based on EPA rulings last year and even the year before. In the next slide, we will see how the safety is addressed by ASHRAE. Until 2021, it was 2 standards regarding refrigerants and safety, Standard 15 and 34. They were old, they were more than 100 years old, and you could tell when you read them, they were difficult to understand and read sometimes. So about 2022, ASHRAE revised them a lot, and they broke out the residential part of it. So now it's standard 15.2, brand new in red there, that addresses residential. But then they have added over the years, the couple of years, all the addendas. An addenda is basically a separate document that where they address errors or improvements or corrections in general. So a couple of years ago, it was those standards plus 200 pages addenda, 400 pages of information. Last year, they cut it down. They included all the addendas into the 2024 edition to make it a little more reasonable size-wise, but the addendas are still being added as we speak, a couple of them already this year, and more is coming. We need to remember that these standards are application-based standards. They are not equipment design guides. But on the next slide, we can see what's applicable for standard 15. In yellow, you can see that ASHRAE Standard 15 doesn't apply when standard 15.2 applies. Otherwise, standard 15 should be used. And in the top part there, you can see how standard 15.2 is defined. It's for single dwelling units or sleeping units, 1 or 2 family dwelling and townhouses, individual dwelling units and sleeping units in a multi-family dwelling. So good examples are dormitories, hotels, multi-unit apartments, and private residences. Standard 34 is basically a list or a classification of all these refrigerants. The next slide, we have a summary of all these. There is an application guide we put out. It's 20 pages, and it summarizes those 200-something pages of those standards, which can be done because we focus on heat pumps, on R32, and indoor comfort. We don't do chillers, we don't do rooftops. That's what we do. And then we can clean up and delete a lot of information and put it in a document. So that document is available on Access. I'm going to give you the QR code for that document a little later. Unfortunately, though, there are some of the various interpretations. They're not clear. Sometimes they're actually contradicting each other within the standards and between the standards. So it can be challenging to read this, but we're going to try to help you to do that in the next slides. So on the next slide, you will see the local codes, how they work with this. ASHRAE Standard is just a document, but eventually it's going to be an IMC or other model codes, and there it trickles down to city or state code. And that's when we really need to use it. It's important to remember that the local code or adopted code shall take precedence if there are differences between the local code and an ASHRAE standard. What we have on the local code, that's more important. The next slide, you will see a good web page that ASHRAE put together, and they update this regularly. So you go to that, there's a QR code there. You're going to get the QR code later again, but I did that, clicked on Texas, and then I get listed on the left. I see states and parts of the state and cities where I can click further and go down and see what the local code would be in that city or that area of the state. So that's very useful because at the end of the day, that's what we have to work with, what have been adopted locally. Next slide. We recommend those 5 basic steps to verify compliance. First of all, we have to determine the releasable charge, MREL. I use the standards abbreviations, MREL, and that's the releasable refrigerant charge. Determine occupancy classification, also needs to be done. It's relatively easy in general. Then we have to determine the VEFF, the dispersal volume, and that's the room volume where this leak could happen. And when that's done, we also need to determine EDVC, that's effective dispersal volume charge, and that's the maximum allowed charge. And then the last step will be to compare those two, the VEF with EDVC. Let's take a look on the next slide, how we address the refrigerant detection sensors. Next, please. There. So we talk about MREL and MS. They can be the same thing. But MS is the total system charge. If we put in shut-off valve kits that are controlled by sensors, then it can be MREL. So you could put in a shut-off valve in the middle of a circuit perhaps, or somewhere, and Wayne will discuss that much better in a few slides. Put that in. So if you have a leak, you shut off a part of the circuit and you're going to have less refrigerant leaking out. And that's the difference between MREL and MS. In many cases, it's the same thing. Next slide. Occupancy classification for us, and the purpose of this presentation, it's straightforward. It's institutional or not. If it is institutional, we're going to allow only 50% concentration compared to the rest of those classifications. Institutional is defined as a part where the occupants can't leave easily by themselves. Think about hospitals, nursing homes, prison. Typically, they can't leave without help from someone else. Next slide. So we need to determine first the VEFF. And we always need to look at the smallest room where this leak will be. That's the most critical, so the smallest room of any rooms. We also, the standard defined the VEF of a room. It's established by the walls, the ceilings, the windows, and doors that can be closed. Doors that can be closed, very important. If they can be closed, it is a wall, technically. And then a partition extending to more than 5.5 feet above the floor. Also important, if you have a cubicle environment and you have high walls between the cubicles, there could be separate rooms if they are above 5.5 feet, especially if they have some kind of door also. The bottom, it talked about the room height. It should be the lowest point of any opening in the supply air duct, the return air duct, or the equipment providing air circulation. The heights can't be less than 2 feet or more than 9 feet. Whatever height you have to stay between those two numbers. The next slide. We can also have connected spaces. If you look at the left there, we have two rooms with a wall in between or some partition closed. And then I have in the top room, I have an air conditioner wall unit perhaps. And it's going to, if it has a leak, it's going to end up in room A. But I could put in an opening between those two rooms, and then I can include room A and room B in that calculation of the room volume. Standard 15 is specifying the opening. You can see that in the middle, case 1, the blue one. Anything below 1 foot can be used. So in that case, I have a 2-foot opening, and that's the net opening. But if half of it sticks above, so half is above 1 foot, I can only use the part that's below 1 foot. So that means I'm going to have 2 square feet in that case. If the whole opening is above 1 foot, can't be used. Then it's too high, which kind of makes sense because the refrigerant is going to be heavy. And this is important because if you look at the right, standard 15.2 is saying the use of doors with transfer grills or undercuts cannot be considered sufficient. So they're saying you can't have door undercuts, while standard 15 saying you can. You can actually have 1 foot undercuts and you would be good. And that's important too, because we have to pick one standard, standard 15 or 15.2, and then stick to it when we do this. We can't pick the easy or the good parts of one standard and then take some other parts from another standard. We have to follow the one. On the next slide, I'm going to give an example, and that is from the application guide we have discussed already a couple of times. Top right corner, you can see the formula in the standard. I don't really like it. It's too many factors included there. So I simplified it in a chart instead in that document. On the bottom horizontal, we have the actual area of an individual room, of the smallest room, where this opening might be applied. I go up and I'm going to hit the purple in this case. I go out to 15, and that is where I have the area, the net area of that vent. In my example, I picked the purple because that is an MREL of 50 pounds, and the M room, the maximum for the smallest room, is 25 pounds. If I go further up, I continue up to the green one. It's going to be a much bigger opening because in that case, I have 75 pounds instead of 50. So the opening is twice as big. It's 29 square feet, which is like 2 doors or something. So you can get the feeling here for how big the net area for that opening should be if you want to use the connected spaces when you calculate the room volume. On the next slide, the connected spaces, if we need to look at the whole air distribution system, the whole thing, and determine the worst case scenario if you have a leak. Interesting is that the volume of ceiling or floor panel can be included if they are a part of the system. If you look at the top right, I put a ducted unit above the suspended ceiling, but it's ducted in and out, so we can't use that area above there, the room height and the volume above that suspended ceiling. But in the lower part, you see an example. I took out that return duct, and then suddenly that space above the suspended ceiling is a part of the duct system, and we can include it. But we can't use more than 9 feet there either. So if the suspended ceiling is 9 feet, you don't gain anything by taking out the suspended ceiling or do something with the ducting. 9 is the maximum number. On the next slide, we're going to see how we can apply this. We have determined the VEFF. That's the effective dispersal volume. We discussed how you determine the area and the room height. Then we're going to have a volume. In this example, I picked 10,000 cubic feet. And the horizontal axis, I go up to the black line there, go out to the left. In this case, black is 0 CFM. It's no ventilation in this room. It's air circulation, but no ventilation for dilution. So I go up and hit the black, I go out to the left, and I see 96 pounds. If I don't have ventilation, that room would allow 96 pounds. That's how we determine EDVC. If I go further up, I can go straight up and to the yellow line, that's 1000 CFM. I go out to the left and I get 134 pounds instead. So that's telling us that if I have 1000 CFM in that room, I gain 38 pounds in the allowed charge because I'm adding ventilation, and that's proportional. So if you do 500 CFM, is going to be half as much, it's going to be half of 38. Next slide. So when we've done all that, we just have to look at the MREL and make sure it's below EDVC, and if it is, we comply. But on the next slide, we're going to look at the RDS. I'm going to call it RDS. In some cases, we can call it LDS as well. The standards are inconsistent there, not really clear. But for the purpose of this presentation, we use RDS. They will work the same way in this case. So an RDS will be required if we have more than 4 pounds in the system and duct openings below 5.9 feet. Then we need an RDS. If we have institutional occupancy, we always need RDS. Whatever is going on with heights and volumes, you always need that. Or if you duct systems, as you can see in the figure there, I can have a ducted unit supply air to 2 rooms. If I have an RDS, which our ducted units have, then I can use both those floor areas, add them together and use them as dispersal floor area. So that would be when RDS is needed. On the next slide, we can see mitigation action requirements. The standard specify that within 15 seconds and at least 5 minutes after the signal has been reset, actions should happen. We need to energize the air circulation, or if we have considered that when we determine the EDVC. We should open zoning dampers. We should activate mechanical ventilation unless it's running all the time. Then it could be triggered by the RDS. We should, of course, de-energize electric resistance heat in the air duct. And if we have those shut-off valves, we should activate those with that RDS. The next slide. Piping is discussed in several pages in this standard. I'm just going to mention that we need to be careful with the height. They shouldn't be below 7 feet 3 inches in open passageways, exit stairways. It's more into how you where you put the piping, but that's very important because that's exit stairways. It's all about safety. On the next slide, we have a discussion about pipe shafts. The standard says that refrigerant piping that penetrates 2 or more floor ceiling assemblies shall be enclosed in a fire-resistant rated shaft, according to the building code. So 2 or more floor ceiling assemblies, meaning that you go through 1 floor up to the next floor, you're good. If you go through 2, then you need a shaft. That's the way it should be read. You don't need a shaft though if the maximum leak is less than 4.8 pounds per 1,000 cubic feet in that shaft. And also if the piping is located outside and vented to the outdoors. The shaft should be insulated. The standard says insulated. It doesn't say how and why, to be honest, but it should be insulated. And then it could be either naturally ventilated or mechanically ventilated. If it's naturally ventilated, you need at least 4 inches diameter. Lowest point should go to the outdoor, which makes sense. Refrigerant goes out, and we also need an opening at the top for makeup air. It could be mechanically ventilated. Then the standard specifies the minimum air velocity in that shaft depending on the area of the shaft. It also needs a makeup air opening and then continuous ventilation or ventilation started or triggered by that refrigerant detector. Either of those would work to get ventilation to the shaft. On the next slide, I'm going to spend some time on a new tool we put out a few weeks ago, a month ago. We call it 3C, Charge Compliance Calculator. If you go to that under the Tools tab on Access, you have to log in, you get that this is what you're going to see. And I'm going to discuss this, some sections of this on the next slide. We can see how, what you will, the top part of it. You can click there to get the application guide that I discussed a few times already. Or you can click and get access to tutorials, how you use this charge compliance calculator. Next slide, we have some inputs. I put in the project name demo. I picked R32 on the left there. I could pick another refrigerant. I have those 6 listed there. If I picked 454B, it would be a little different result because there are a few percent difference in the limits between these refrigerants. But I picked R32. Top middle, I acknowledge the disclaimer. There's a disclaimer, of course, with this calculator. Top right corner, I picked the imperial units. Could do metric to Canada perhaps, but I picked the imperial. And then in the middle bottom, the question is this for a residential application? I said no. If it is residential, I would say yes, and then we get other inputs to do on the following slides, but I said no because we're going to focus on non-residential stuff, and that is standard 15. So next slide. Here you can see the inputs. I'm going to discuss those real quick. Top left corner, I picked 38 pounds. I thought that was a good number for this example. There's a range for that. If you are outside the range for your inputs, you get an error message and it wouldn't be accepted. The range you can see there, you get that if you hover about that question mark. Dispersal floor area, below there I picked 950 square feet. And then system with ventilation, I did 200 CFM. If you have no ventilation in your system, you put in 0, I put in 200. On the right, top right, I picked the occupancy classification public. Dispersal height, 4 feet. It's kind of a weird height. It's not the floor unit. It's probably not the ducted unit, but I picked 4, and you will see why in a few slides. But let's assume it's a wall unit that sits halfway up on the wall or something. So 4 feet is the dispersal height for this example. Do we have safety shut-off valves? I put in 0 because we don't have that yet. I could, if I have that, I will put in the charge that we will get because of those. On the next slide. A couple more questions to answer. Do we have any duct openings below 5.9 feet? I said yes, we have that 4 foot height. So I said yes on that. It's either no or yes there. Do we have ventilation for dilution or air circulation activated by RDS? I answered no. And then a couple of reminders. Have we looked at the RDS requirements in the standards? Yes. Is piping requirements reviewed? I said yes. So with all those inputs on the next slide, we will see the output. This is the results with those inputs. Leak detection is required because we have the 4-foot unit sitting, and that's below 5.9 feet. The charge was 38 pounds straightforward. In the red there, you can see we have an EVDC value. Because the ventilation, we get 7.6 pounds extra. But the total EVDC value for this, including those 7.6, is 43.9. So that is the maximum allowed with that ventilation. So it means we are in compliance. 38 is below 43.9, so very good to go. If you want to have a report of this, you would click on Export PDF there, and that will give you an output page that we'll take a look at. Next slide, please. Let's say I changed my mind, I didn't have ventilation. Then I get the result that's not good. It's all red. And that's not fun, but the fun starts here actually, because then you could put back in the CFM. There you can see in the lower green there, let's say I put in 200 CFM or 100 CFM might be enough to comply. I could change the refrigerant system charge. Perhaps I could relocate some piping or unit, get a little less charge, and I could keep it below those 36.3 in this case. Probably not changing occupancy classification, but the dispersal height could easily be changed. Let's say I put that wall unit at 6 feet instead. That probably give me enough room volume to comply with to be able to do those 38 pounds just by moving that one. I also didn't put in shuttle valves, so that's why it's 0 there. But perhaps I put in shuttle valves, I could limit it to much less that could leak, and that could make me comply. Dispersal floor area, I don't change that. But let's say we had another room adjacent to this room, we could put in a natural opening and get benefit from that room area as well. So, and that's the beauty with this calculator. You do your input and then you see if you have to massage something to get the output you want. The next slide. This is just the report, the output page. You can see the inputs we did and the comments about the inputs, and then we also get the result at the bottom. Okay, and now, Wayne, it's your turn to take us through some really informative examples.
Why, thank you very much, Leonard. I really appreciate that. And I would like to emphasize how critical it is for what Leonard just discussed to determine the effective dispersal volume, or VEEF. That is a key part of the equation. So next is the refrigerant charge. So Leonard talked about the effective dispersal volume charge, the EDVC, like how much refrigerant can that volume safely contain or manage. So the next part of the equation here that we're going to discuss is how do you determine the system charge? Well, as we know with Design Simulator, we can do that very easily. If you notice on the top, I've got LDS as well as RDS introduction. So as Leonard mentioned, RDS is a term that's used interchangeably with LDS, and I'm going to put the emphasis back on LDS simply because that's what you will see in the majority of our literature. My half of the presentation is going to be Design Simulator based. We're going to cover the LDS devices that we have for VRF that are available today. We'll talk about how to apply those in some three different primary scenarios, and then we'll get to the ever infamous maximum releasable charge calculation, MREL, as you see on the bottom, which is in red. And I've got a note here it's going to be an abridged version because the actual calculation is quite complex, which is something we are working on, which we'll discuss. So what is Design Simulator? Chances are most of you are very familiar with it, but it is a proprietary equipment selection program designed by Fujitsu General Limited. It provides a complete bill of materials, capacity data. There's a significant amount of resourceful information which the reports provide, but we're going to focus on the refrigerant charge data because that's the next part of the equation to make sure that charge will be compliant with the ASHRAE standard. Now, just so you know, Design Simulator covers H-Series, and I mention that because how many times do we see our H-Series systems used in light commercial applications? We see it quite a bit, actually, don't we? So as long as it's a bona fide ASHRAE 15 application, then we would fall under the, just because it's H-Series doesn't automatically mean it's a residential unit that goes by, say, 15.2. So the point is here, Design Simulator fully supports H-Series systems where we can input our piping lengths and come up with the charge. Now, if you notice the bottom bullet point there, that about 80% of our H-Series systems have a charge that's 4 pounds or less. So that means for a majority of our systems, we won't even have to worry about ASHRAE's standard compliance with our H-Series systems when they have 4 pounds or less than refrigerant. So that's you can wipe your forehead there. So remove some of that sweat and anxiety, because it's not going to be an issue with the majority of our H-Series systems. Design Simulator will provide in the reports a detailed estimate of our total refrigerant charge. For example, as you see here, the refrigerant in the outdoor unit's 5.9 pounds because of the piping an additional 4.1. So on the lower right, we have a total charge of 10 pounds. We know we're over 4 pounds. We know that we have to factor for dispersal volume and then let the games begin. But at least again, with Design Simulator, we'll be able to know right off the bat whether or not, and this is in the pre-planning stage, I'd like to emphasize that, because if the charge is not compliant and it involves some additional accessories, you definitely want to have that accounted for in the project bid ahead of time instead of afterwards. So when we say LDS, what exactly does that mean? It means leak detection system or refrigerant detection system. So as you can see there, and under the J series column, we have 3 components that are available again today.
We have a wall mount gas sensor, shutoff valve kit, and expansion kit. Now, as Leonard had mentioned, all air stage ducted units include a factory installed leak sensor, which is internal to the cabinet. However, this should not be confused with the gas sensor kit that is an accessory option.
Another function of Design Simulator is to select the LDS accessories. And the reason I mention this is because, of course, if you're designing any VRF system, you definitely want to use Design Simulator. What's nice about Design Simulator is it will not let you have a misapplication on the equipment side. Likewise, on the LDS selection, it will not let you make a mistake, as well as it provides the available accessories for the indoor and outdoor unit. My point is, you don't have to worry about memorizing these components. I think, like anything else, through repetition, they're going to become second nature. So we are talking about the ASHRAE safety standards, but there's also an equipment standard that we as a manufacturer have to go by. You've probably heard this before, UL 60335. So this dictates how the equipment shall perform in the event of a leak and what the components shall do. But there is also another feature that I'd like to mention here within Design Simulator that we talked about on VPX3, which is the ability for Design Simulator to basically tell the user whether or not their areas will be, where the charge will be compliant relative to the specific zone. So I go through step-by-step measures in VPX3. We have a recording of that if you wish. But just a quick summary here, you see on the inset, in this case, we have a 4-ton J7S system where it shows that zone 1, it's not compliant. In other words, the effective dispersal volume is too small. So what's the response that we need? Response measure 1 is we need to initiate air circulation, which would be triggered through a leak detector, which the third response would be because the circulation alone is not sufficient. So therefore, the response measure 3 is either ventilation or shutoff valve. Now, I point this out because it will not tell you which measure to take. That's up to you, the system designer, because we can do one or the other or both. So if there's an ERV on site, for example, perhaps we could take advantage of that. Or if not, maybe we want to go with a shutoff valve only. But we'll take a look at that. So new LDS items. Again, Vikas did a great job in the last VPX to cover these components. So as a quick review, we have 2 shutoff valve kits that are sized based upon how they are used relative to their shutoff application, as well as if they're used on the inside based upon their capacity. The gas sensor kit and the expansion kit. So we'll unpack this here a little bit. Those of you VRF veterans will look at this and say, I know what that is. That's an RBU. We use these in heat recovery systems all the time. Well, it looks like an RBU, smells like an RBU, but it's not. It's a dedicated shutoff valve that has actually 2 inlets and 2 outlets. That's 1 per liquid line, 1 per vapor line. So it's a dedicated shutoff. And it's interesting to note that we use EEVs. So we don't use the EEVs for the sake of creating a pressure difference for, change of state like we would in an indoor coil in a cooling mode. Rather, we use the EEV in a solenoid-like application where the EEV is always going to be either fully open when the system's okay, or if there's a leak event, the EEV will drive fully closed. We have an expansion kit, which I refer to as a wiring hub. So anytime you use a shutoff valve on the what we call the indoor unit side or partial shutoff, the expansion kit's going to be required. Likewise, as you see on the second lowest bullet point there, as a ventilation interface. So if you are to use third-party ventilation, we have means for inputs and outputs that we'll talk about here shortly, as well as an alarm output. So say, for example, if there's a leak event, you want to have a third-party audible alarm or a visual alarm, we can do that. That's limited to your creativity. We have a gas sensor kit. Now, keep in mind, again, this is the option for J series for right now. It is a wall mount device. It can be used with or without the shutoff valve upon our application. For example, if you're only initiating ventilation without a shutoff valve, then we would need, of course, something to detect the leak. So the connection points, it connects to the indoor unit directly in cases where we are not using a shutoff valve or a partial shutoff. It requires a separate UART cable, or if we are using shutoff valve kit and a partial, it would connect to the expansion kit, which does not require any special cables. So here are terms that you will see in our literature over and again. That's either whole shutoff or partial shutoff. I'd like to preface this slide by saying you will never see exactly what you see on the screen right now. That is, you will never see a whole shutoff combined with a partial shutoff at the same time. It's always going to be one or the other. Now, you may hear the whole shutoff referred to as the outdoor unit side. Of course, it does not connect, does not get connected to the outdoor unit. It still has to be in an indoor location, but it physically wires to the outdoor unit.
Thus, as the name implies, a whole shutoff application will isolate the refrigerant charge for all indoor units and refrigerant piping downstream of the kit.
Anytime it's used in a whole shutoff scenario, regardless of outdoor unit capacity. So even though we have a 2-ton, 4-ton, we would still use 0.60 in a whole shutoff. The advantage is, of course, it's simplistic, but the downside, you might say, is it has the least effect on the maximum releasable charge. So if you're isolating all of the indoor units, of course, effectively your charge reduction, your releasable charge reduction is going to be potentially minimal by comparison. But that may be all you need. Perhaps you may be only half a pound or 1 pound or maybe 2 pounds from having your charge compliant for your system. So in this case, we see the total system charge of 10 pounds, 10.1. And using this approach, we can drop it by about 2.5 pounds to 7.5 pounds. So on the opposite side of that, you might say, is what we call a partial shutoff, where just as the name implies, we're not shutting off refrigerant flow to all the indoor units, but only to the select indoor units. For example, if we had indoor units 1 through 4, where the effective dispersal volume were sufficient, but only the smallest unit there was not, we could apply a single shutoff valve to only 1 unit and thus have the charge reduced significantly, as we will see. One of these items needed the expansion kit, as I mentioned, that anytime you're using it in a partial shutoff, you will require the expansion kit. But as the 2 bullet points show, we can use this for ventilation output as well as alarm output. So if we're going to initiate a third-party ventilation, that signal does not originate from the indoor unit. It's actually from the expansion kit. So if you look on the right, I've got a kind of a blown-up view of the terminals on the expansion kit. So on the lower of the 3 green boxes there, the P71 is our connection points for a shutoff valve kit if we are using it. The middle one here is an external out for an alarm. That's P587. And then the top one, P586, is ventilation output. So there are no special cable accessories required for that, which is nice. And I will mention that those of you that are, again, familiar with VRF know that our other external outputs, they are 12 volts DC with a max holding current capability of 50 milliamps, of which our typical RIB relay works perfect, the third-party RIB relays. So we could use a third-party or rather we could use a rib relay to initiate a third-party ventilation sequence upon a leak event, for example. So the gas sensor, as I mentioned, it's going to be required anytime we have a shutoff valve, regardless if it's on the outdoor unit side, if it's a whole shutoff, or if it's on the indoor unit side for a partial shutoff. Now you may say, well, wait a minute, I thought you said that the ducted units come with a factory installed gas sensor. Well, they do, and they are sufficient for triggering circulation only. However, if you're adding a third-party device such as ventilation, or if you are using a shutoff valve, you do need the gas sensor accessory. So just something to be aware of. And another thing that I think you should be aware of, and because I had covered this in this presentation as well, but with the gas sensor, for example, the first time I saw that, I thought, oh, this might be, perhaps confused as a remote control or a thermostat, if it's 5 feet up on the wall. But no, it's, as Leonard mentioned, because of the density of the refrigerant gas, it's about 1.1 times heavier than air, so it'll tend to settle. So the top of the sensor should be not greater than 1 foot off the floor, with about a 32-foot radius from the center line of the indoor unit. And if it's a wall mount, it should be on the same wall as a wall mount, for example. And if we can make that clearance, it can be reduced to 22 foot if there is an obstruction, for example, such as a table in between. Now, it's so nice, let's say it twice. What's the definition of MREL? It's a maximum releasable charge, which is a portion of the refrigerant charge that can be released into the space as a result of a single point failure. And that unit of measure is pounds, of course, or kilograms if you're working with a metric system. So MREL, again, maximum releasable, or you may hear us just say MREL. So if you're MREL, now MREL is only going to be effective when we use a shutoff valve. If we do not use any shutoff valve in the system, MREL will not exist. MREL only comes into consideration when we use a shutoff valve, again, to quantify the downstream refrigerant charge. So again, we have a whole shutoff example, which again, as you see here, will isolate all of the indoor units. And within Design Simulator, it's critical that you enter in all of your, either your estimated, preferably if you're working in the planning phase, you'll put in your estimated piping lengths. And then that way we'll be able to determine our total refrigerant charge as a function of all the downstream piping to include our indoor units. So partial, I think you'll begin to see a pattern here again. So instead of isolating all the indoor units, we're isolating only a single indoor unit, or units, plural, as in a group. We'll take a look at that in a second.
So when the estimated or actual piping lengths are entered, Design Sim will provide the piping length as you see in the lower left inset. The total cumulative piping length is 185 feet, which is a one-way measurement, that is, and then you'll note the red arrow that indicates the actual piping length, which is along a single unit run between the outdoor to indoor unit. So in this example, we see a 60-foot run from the outdoor unit to the header and 75 feet from the header to the indoor unit. Remember too that the piping reflects linear lengths, not equivalent length from any fittings. Now when using a shutoff valve kit, you will see there is an additional length that needs to be entered, that being the distance from the shutoff valve kit to the indoor unit. This length is not in addition to the 75 feet, rather how much of the 75-foot segment is from the shutoff valve kit to the indoor unit. So as you see, using a partial shutoff can offer a significant advantage of reducing the max releasable charge compared to a whole shutoff valve kit option.
We can do grouped indoor units, for example, very similar to how you group indoor units from a piping perspective. We can also group indoor units to a shutoff valve perspective. So what you see here is 2 indoor units. For example, if they are 2 indoor units which serve the same zone that would be within the same area, for example, you could group these 2 together, and it would be depending upon the layout, whether you need 1 separate wall sensor or 2. Here to illustrate the point that we can do grouped indoor units. So it does not have to be just 1 indoor unit on a partial. We can group indoor units and then have a grouped shutoff valve application. So now we will get to what you all paid for today. You paid for your whole seat, but you're only going to need the edge because it's that good. So that is the maximum releasable charge estimation. Now the MREL value is actually used for both standards, which is interesting. Again, when you think about it, what are we talking about? It's the amount of refrigerant downstream of a shutoff valve that can leak in the event of a single point leak. So if we had a leak at the indoor coil and the valve shut off, how much refrigerant are we going to lose? So we're going to look at it by the numbers here. First is the shutoff valve. the refrigerant volume there. Number 2 is indoor coil volume. We will look at the liquid line as well as the vapor line. And then number 5, which I have in gray here, is the shutoff valve closure time, because there are some numbers that you might say are a bit nebulous, that are not practical for us to calculate in the field, that are a value or variable in terms of how much refrigerant could be released. However, by far the majority will be a combination of 1 through 4 above. These are the values that you would not be calculating, but it is something that is done in the background once Design Simulator will be able to provide this information. So by the numbers here, number 1 is, when you think about it, if there's a leak, how much time occurs from the point at which the leak occurred to when it was detected. And then number 2 is how much refrigerant leaked from the time that it was detected until the shutoff valve closed, for example, or closing. So let's jump right to number 5 on the bottom right there somewhat, where it's a summary of the refrigerant pipe volume of refrigerant. So when you think about it, again, liquid and vapor, times the refrigerant density, which is going to differ depending upon if it's a liquid or vapor, as well as the refrigerant type. But we're talking about R32 here. First one, again, by the numbers, we'll take a look at the shutoff valve. So the shutoff valve holds, it's dependent upon the model number. So in this example, we're using the 027 model, which again can be selected through Design Simulator. So we see that it holds about 1/4 pound of refrigerant. That's pretty straightforward. Next is, what about the indoor coil? We call them heat exchangers. So how much refrigerant is going to be contained within that coil? And there's an interesting aspect here to how ASHRAE calculates this. Now, if you'll notice on the source on the screen, I show 15.2 because 15 does not actually specify these values, but it is within 15.2. And again, the MREL value is used in both standards. Now, you'll see MU and then a subscript with the letter H that's in red. And I did that because there's 3 modes, effectively 3 modes of operation. If the system is running and you have a leak, it could be in heat mode, you could have a leak in the cooling mode, or you could have a leak if it's in standby. So we have 3 different scenarios that ASHRAE defines. There's MUH, for example, for heat, MUC for cool, MUS for standby. So what I did here is I picked the larger of the values just to be, again, on the conservative side. And it tends to make sense when you think about it. In the heating mode, we're using the indoor coil as a condenser coil. So chances are the coil is going to be most effectively flooded in the heating mode. So in this case, we have an 18,000 BTU unit. And if you look at the column on the far left, it says 18 to 24K. We're going to use a set value of 2.4 pounds. Now, I will mention that this is subject to change. You'll see the asterisk there, because I will tell you, as of today, Design Simulator is not capable of calculating the MREL value. However, our engineering team is working on it. We do have a development timeline, so that will be something that Design Simulator will be able to calculate, that will be released later on this year. Next, we're going to take a look at our liquid line volume, and I've added in 2 different sources here. So if you see the 1/4 inch row, you'll see that it says 0.013 and 0.011. The 0.013 is our design and tech manual, or as well as our installation manual. So we have 0.013 pounds per foot that we use, that we factor for determining refrigerant charge. Now, the ASHRAE standard shows 0.011. So just to give you an idea of how close ASHRAE and our sources are. So if you think about it, that's 0.002 of a pound per foot. So there's not very much refrigerant. To factor that out, a 50-foot line set, 1/4 inch, would be about 1.5 ounce difference. So again, really, it's negligible for the most part. So since we know we had 15 feet, we would multiply that to obtain how much liquid we need to factor. Now, on the vapor side, we don't provide any published information just yet for this. So for right now, we will thus default to the ASHRAE standard. Again, here I put in 2 different values to take a look at, just for illustration and understanding purposes. So G for gas, we have MGS for standby, and MGH for heat. So you will note that, for example, in a 5/8, well, actually, since we're dealing with a 1/2 inch line, we'll use the 0.004 because it's in the heating mode. So times 15 feet is 0.06, or 0.06 of a pound. Again, very, very small amounts. But it's interesting to look at the larger the line, the greater that difference becomes. So for example, a 5/8 line is 0.025 pounds per foot compared to 0.006 in the heating mode. But here too, again, even say if you had a 50-foot 5/8 vapor line, factor out the difference between the two, and it's only a few ounces, really, like 5 ounces. So again, the total charge difference between whether you're talking about standby or heat is minimal. What becomes significant is how much does the coil hold within the heating mode, cooling mode, or standby.
Looking at the MREL value, which is a total of the individual components we just discussed, the shutoff valve, the indoor unit heat exchanger, the liquid and vapor lines, we see a total of 2.9 pounds, which is about a near, I'd say 70% reduction compared to the MS or system charge. And if you recall, in the whole shutoff valve example, we had a 7.5 MREL value. Thus, the whole shutoff has about 40% higher releasable charge than a partial shutoff, again, at least in this example.
One of the tools that's in J7S that we are going to consider adding is an MREL calculator. Now, this will account for the values that we discussed before, that is 1 through 4. This does not factor the valve closing time and such, but again, that's a minimal amount. So in lieu of providing nothing, at least we can have a calculator it's a PDF document with the fillable fields. You just simply enter in your piping between the shutoff valve to the indoor unit, how many units based upon capacity, and the shutoff valves, and it will provide for you an estimated MREL value. And one more point here is on the indoor unit capacity, note that the factor that we use for the indoor units is not a function of the unit, whether it's a cassette or wall mount or ducted, but rather by the unit capacity. So for a quick summary, Design Sim should be used for every R32 application, whether it's J series or H series. I'm a firm believer in that. Why? Well, you want to make sure that your refrigerant charge is in compliant with the safety standard that you're using. In this case, we were talking about standard 15. It's a permanent record that can be used for your authority having jurisdiction, combined with the export PDF that Leonard talked about from the 3C calculator. You can create infinite what-if scenarios within Design Sim, avoid costly errors, make sure that you get it right before the installation goes in, and then, well, everybody will be happy. Now it is back to you, Leonard.
Thank you, Wayne. Very good information. I have only 3 slides at the end here. I try to squeeze those in. So if there is a solution you have and it doesn't comply, there are ways to look at that. Basically, it's an imbalance between the room volume and the refrigerant charge. So there are ways to kind of increase the room volume. You could put in air circulation with earlier, and that could improve the EDDC value. You could also remove or raise the suspended ceiling, perhaps, if it's below, not above 9 feet. Relocate indoor unit fan coils or even piping. Put in an RDS, then you can combine several rooms. We have seen how that can be done. Then have a permanent opening between connected rooms as well, and ventilation with dilution. You saw in my 3C calculator how that can be done. Also, ways to decrease the refrigerant charge. Install those RDLs that Wayne talked about, would shut off a part of the circuit. Relocate or remove indoor unit fan coils. The same with the piping. Can also, if you have a bigger VRF system, split it in 2, then you will have less charge that can leak. Replace or move fan coils, and also use adaptive zoning system for several zones could also help you to decrease the refrigerant charge. On the next slide, I'm going to try to summarize what we have discussed. ASHRAE Standard 15 should be used in all cases except when 15.2 applies. MREL should be below EDDC, then we comply. And in short, RDS will be needed if we have a system inducted above 4 pounds charge and less than 5.9 feet above the floor. Ducted systems where spaces are connected to the same, you saw that example with the same ducting, then you can use an RDS to include all those areas. Or if we have shut-off valves, air circulation, ventilation initiated by RDS, then we need an RDS. And also if it's institutional occupancy. To the right, you have a reminder about the local code, how the adoption process goes. We need to make sure we have the right local code. You You can also see the front page of that application guide we discussed a couple of times. And on the right, you have the 3C, that's the calculator that is available on Access. So thank you. This is the QR codes we have discussed. You can see the application guide on the left. The building map code, the ASHRAE, is the next one. The application for Fujitsu application library, a lot of good information there. Fujitsu Training Academy has a lot of good classes specifically about R32. And if you have questions, you can always send it to application support@fujitsugeneral.com, and then our application team will answer them and help you out there. So thank you. I think we're running out of time. Vikas, do you have anything to say at the end?
Thank you, Leonard and Wayne. Great job. So I don't see any questions at this moment, and we are right on time. So again, I thank you everyone for attending on this afternoon, and have a great day. Thank you.